Hi everyone, my name is Daniil. I'm from Yandex Cloud, working on Valkey, and today I wanted to present a quick talk about our quest of speeding up Valkey by 10 to 12% with minimal code changes. Actually, it was about 10 lines of code. So we are going to be talking about Valkey. So I'm going to make a small remark about what is Valkey, what was lacking in observability of Valkey, how we are actually gathering latency stats for observability, why it resulted in conclusion of knowing exact time is expensive, and how can we make clocks faster, actually. And the most important thing is benchmarks. So a little bit about Valkey. Valkey is in-memory key-value database. It is BSD licensed. It's a fork of Redis, backed by Linux Foundation, and actually executes client commands in a single thread. If you actually run Valkey and look on the Valkey process, there is a lot of threads, network I/O, disk I/O, background tasks, but only one thread actually executes commands. A little bit about main thread and its execution of commands. All commands are executed sequentially. Sometime we spend actually executing the command, and sometime we spend writing that data to socket for user. There's also a little bit of housekeeping to be done, expiration, eviction of keys, and etc. Also, you can send a couple of commands in a single packet. You can pipeline them, not wait for a result of a previous command. Here, for example, we send 3 commands and we will get results for 3 of those commands in a single response. So what was lacking in observability? Due to busy looping in event loop, utilities such as stop showed almost 100% CPU utilization, even when there was a lot of time to execute more commands, actually. So how can we shed light on those blind spots? We can measure duration of active loop iterations, and by comparing that duration against the elapsed time, we can determine what percentage of time we are actually doing useful work as opposed to waiting. So what I learned along the way, we are actually already measuring the duration of each loop iteration, and we do this by calling get monotonic microsecond function. And under the hood, for the most build, this function translates to POSIX clock get time call, and this is definitely not taking a lot of time, right? At first, there were no particular concerns that this function would be very slow. There are infamous Linux optimizations with virtual dynamic shared object that help us not do the full context switch and execute some of reading of clocks in user space. But there is no such optimizations for monotonic clock, and I want to make a small remark here. For most of clocks, there is an optimization in Linux that helps us not do the full context switch. But after reading the kernel code, I concluded that there is no such optimization for monotonic, and a decision was made to use a processor clock, a time step counter on x86 and CNT VCT on ARM. This essentially is just reading a special counter register on the CPU. Now let's build with CPU clocks and run some tests. And somehow tests are failing. Looks like time started to go faster than it should. What's causing it? It turned out that TSC frequency on x86 platform was determined from the processor model. And the processor model may sometime include marketing frequency. That is actually not a frequency processor is running on. So reading from it resulted in 2.5% higher frequency for the time step counter than the actual. Earlier in 2025, others case added a calibration for CPUs without frequency in the name. Let's always calibrate, even when the CPU contains frequency in the name. So what performance benefits do we get from CPU clocks? A couple of instructions in a user space instead of full syscall provide an order of magnitude speedup. Full syscall with context switch is about 100 nanoseconds, and reading CPU register and doing some mathematical tricks to it is actually a couple of nanoseconds. And in synthetic benchmarks, this translates to almost 200,000 RPS more. And this is about plus 7% on reading workload with 9 IO threads and pipelining of 10 commands. Now that we have fast monotonic clocks, what can we do more? Thanks to Victor from Ericsson, we can cheat a little and speed up getting Unix timestamp by caching the value of another syscall, get time of day, and add the monotonic delta between calls. As you can see, this is not a lot of code, less than 10 lines of code, but this one change also results in 7% better performance on reading workload with same pipeline of 10 commands and 9 IO threads. Small remark on the benchmarks. These benchmarks exaggerate the situation where Valkey is bound on CPU, not on IO. In most of real-world use cases, Valkey is bound by IO, and there is actually not that big of an improvement, but we will definitely be faster, and we will be able to serve more user requests and provide smaller latencies. Also, I wanted to share an awesome dashboard that colleagues from AWS made with Percomet benchmarks. As you can see, there are two increases in performance, and the first one corresponds to compiling with CPU clocks by default, and the second one is Unix timestamp optimizations. And as you can tell on this small part of the graph, we get 11% faster read performance with 96 byte values and almost 15% increase with 16 byte values. Those are QR codes to Valkey on GitHub and awesome performance dashboard provided earlier.